All right, hello. This is kind of part two of our, I guess you could say, our really honed in focus on what a periodic function is. And that would be sine and cosine. And how do we graph them? What happens to the graphs of them as we change the parameters a, b, and c? So we left you, after our video that we gave you guys yesterday, we left you with this problem. If our function is f of x equals 5 times the sine of x plus 25, what's the amplitude, what's the period length, what's the maximum height, what's the minimum height? So I've graphed it on Desmos to the right, but before we even consider that, we really actually can determine all these items by just looking at the equation. So as we said in the video, the amplitude is always whatever that a value is, the positive version of it. So we've got a positive 5, right? The amplitude is 5. If that 5 did not exist, we would have an amplitude of just 1, right? An invisible 1. What is the period length, right? How long does it take for you to go up to the maximum, down to the minimum, and back to 0, or back to our x-axis? And that takes, in this case, 2 pi radians, or 360 degrees. We will describe to you today how you can calculate the period length based on the parameter b, which we don't have anything. We're not placing any parameters on the variable x at this point. So that's what this video will be for later. The maximum height, if you think about it, typically you're centered at the x-axis. And even if you have an amplitude of 5, right, you take your maximum and you take your minimum and you are stretching it out by a factor of 5. So you have a maximum height of 5 and a minimum height of -5 now. But now let's vertically shift that up 25. So if you think about it, our maximum height was 5, tack on 25 to that, and you get 30. Our minimum height was -5, tack on 25 to that, and now we're at 20. So just so you can see that it's happening, right? This is the graph of it. Start at height of 25, right? Because that is where we are centered, plus 25, and our amplitude is 5, so we're going to go 5 above 25, and we're going to go 5 below 25. So we start at 25, we travel up to a point of pi halves, comma 30, or I guess you could say that's the 90 degrees, comma 30, that's our maximum. We're going to travel down to our minimum, 3 pi halves, comma 20, and then we're going to get back at 2 pi, about 6.28, right there. That is 2 pi radians. That is our one period, because we went up, we went down, and then we stopped right back at a height of 25. Now, we have talked about some very important vocabulary in this problem. And so I want to go over the official vocab of these. This lesson's objective, or I guess you could say this investigation's objective in the textbook, is how can the cosine and sine functions be modified to represent the variety of important patterns of period change. So the first key term here is a periodic function. This is a new family of functions. It's a function, sine or cosine, that have patterns that repeat as your values of your independent variable increase. Right? So as my independent variable increases, which in this case is measured in radians, so as my number of radians, or my angle measure, increases, my function is going to repeat this exact same pattern no matter how far I zoom out. It's the same pattern on and on and on. So that is a periodic function. Now, the period of a periodic function is what's the length of the shortest interval for which your values of the independent variables on which the repeating pattern of the function value occurs. I butchered that. Let me say that again. The period of a periodic function is the length of the shortest interval of values for the independent variable on which the repeating pattern of the function value occurs. Values occur. In other words, how long does it take to complete one single instance of the pattern, I guess you could say. And our pattern is that we start kind of at our ground, we go up to our max, we cross the ground level, we go down to our minimum, and then we get back to ground level. And that is one, I guess you could say, if we were to translate this to a Ferris wheel, that's one revolution of the Ferris wheel. So how long does that take us? Well, 6.29, that is 2 pi radians. So our period for a standard, right, without having any parameters on the period will be 360 degrees or 2 pi radians. That is kind of our default. The amplitude, it's half of the maximum height minus the minimum height. So in this case, if I take my maximum height of 30 and my minimum height of 20, if I do 30 minus 20, I get 10. Divide that by 2, and I end up with 5. An easier way to determine that is it's just going to be, with our parameters a, b, and c, the absolute value of parameter a is always the amplitude, aka the positive version of a is always the amplitude. And then last but not least, we've got this fancy term called y displacement. That's what the textbook refers to as our vertical shift of our graph. So in this case of our example, it's being shifted 25. Or I guess you could say the y values are being displaced by 25, positive 25. So that is, right, this is the problem we went through yesterday, or that you went through yesterday. Here is the terminology. And if you need to take a screenshot of this so that you have it as a reference, please do so. But one thing in the video that Mr. Lemon and I made yesterday, Mr. Lemon asked me, do we want to talk about what if we put a negative out front? And I said, not today. Well, come to find out, it's actually pretty important, and we should probably mention it right now. So we are going to go to Desmos. And we've got my fancy version here, a times the sine of bx plus c. We've got our parameters, and I currently have it in standard form, right? I'm centered, or I guess you could say I start at 0, I go up to a positive 1, I go back to the center, I go down to a negative 1, and I end at 2 pi. So my full revolution right here, or my one period, is from 0 to 2 pi. So my period length is 2 pi radians. Now we said that when we increase a, it's like we're doing a vertical stretch, right? We're taking this maximum point, and we're taking this minimum point, and we are stretching them. We're pulling on the maximum, we're pulling on the minimum. Now notice our zeros are still the same at 0, pi, and 2 pi, or 0, 180, 360. It does not change. What does change is our maximum and our minimum, though. But our period length has not changed at all. We'll put that back to 1. C, what happens when we do C? It's a vertical shift, right? It's just shifting. Where are our maximum, minimum located? Where is our graph just located? It doesn't shift it to the left, doesn't shift it to the right. It is just simply saying vertically up or down. Now, one thing that we didn't mention yesterday is what if we make this negative? Anybody notice the difference? So going from positive to negative. Positive, notice where the maximum point is, right? The maximum is at pi over 2, but once I change it to negative, my maximum point, it's actually over here at 3 pi over 2. So essentially what this is doing is it's reflecting our curves across the x-axis. Now since we have this pattern, to us it doesn't look that different. But really it's all about where do I start and where do I go. Typically when a equals 1 in our standard form, we go up to our maximum first. That's our first stop. Then we go back to 0, down to negative 1, back to 0, 2 pi radians. When it's negative, we go down first. We go from 0 to our minimum, negative 1, back to 0, up to our maximum, back to 2 pi radians. So when when A is negative, it's reflecting our curve across the x-axis. But now since we've got our curve is on both sides of the axis, there's a double reflection occurring. Now, not to complicate it too much more, but let's say we have this as A. What if I vertically shifted this up a little bit? What do you guys think will happen now? Is it still going to do some type of reflection? And if so, where is it going to be reflecting? Well, if we had this imaginary y equals, looks like since we shifted it up 3, it looks like the center, if I were to put like a skewer through this, it's at 3. So now the line that I'm reflecting over is the line y equals positive 3. So it all just depends on kind of where I guess you could say the middle of our sine function is. That's where it reflects. But in short, it just flips the maximum and the minimums. So if it was a maximum, now it's a minimum. If it was a minimum, now it's a maximum. And that's all important because you have to track all these changes. Because once we start changing B, it's interesting to see what occurs. So A stretches it. C causes a vertical shift up or down. When I make A negative, it causes it to reflect or flip, right? The maximums are now minimums, and the minimums are now maximums. Now, what happens when we change B? So I'm going to move B, and I want you to decide what's occurring when I change B. So as B increases, now I'm going to make these points distinct so that you can see them. I don't know if they'll disappear. But as I change B, starting, make it 2, make it 3, 4, 5, 6, 7, 8, 9, 10. So what's occurring here? Well, it looks like an accordion kind of, right? Or a spring that's contracting and expanding. So if we start with our typical 1, go to 2. One thing that I want you to notice is when our B is equal to 1, our standard version, our period length is, excuse me, our period length is 2 pi radians. When I make my B equal 2, it scrunches it all together, horizontally speaking, and now if I go up, down, and I end up back at, okay, now it's pi radians is my period length. So when I put a 2, right, when I make B 2, my period length shrunk in half. Now there's a fancy formula that occurs here. Essentially, you need to divide 2 pi radians by whatever B is to find your period length. So in this case, if I have B equals 2, so 2 pi divided by 2, that is equal to 3.14. So that equals pi. All right, now what if we make it 3? Well, start at 0, 0, go up to my maximum, through the middle, down to my minimum, back to the start. 2 pi over 3. So 2 pi divided by whatever B is, that's 3. Hey, that's exactly what they're telling me it is right here. That's the simplest form. So this is my radians as my period. What if we went to 4? Start here, go up, through the middle, down, back to the start, pi over 2. Well, 2 pi divided by, what's our B value? It's 4. So 2 pi divided by 4, we can reduce the 2 over 4. That equals 1 pi, so a single pi divided by 2 radians, oops, that's my period. Okay, so now what happens if I made this a decimal? So let's say let's go back to 1. What if I went to half? What if I put this at half? Watch what happens when I make this a decimal. Interesting. It looks like it's getting stretched out. Looks like somebody's taking the end of it and pulling on it, but it's still being anchored here at 0, 0. So it's weird. I'm moving my slider to the left, but the graph is being extended to the right. It's a little bit of an inverse type of relationship here. So what if I had half? Same rule applies. Divide it by b. So 2 pi divided by b. What's b here? It's a half. Divided by 0.5. Well, 12.566. They're rounding that. Well, if you know anything about the decimals, well, 2 pi is about 6.28, right? Because pi is 3.141592. So that is equal to 4 pi radians as my period. Another way that we could look at that is, well, 2 pi divided by 1/2, right? That's the same thing as multiplying by the reciprocal, right? If you divide by a fraction, you're multiplying by the reciprocal. So that's the same thing as 2 pi times 2, and that equals 4 pi radians. What if I made it 0.25? Or actually, let's make it 0.75. Let's make it interesting. So I start here, go up, down, down to the minimum, back to the start. 8 pi over 3. So my b value is 0.75. So 2 pi divided by, what is that, 3/4, right? So divided by 3 over 4. And as I just said, when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So times 4 over 3. And we know that that ends up equaling 4 times 2 pi divided by 3. And we know that 4 times 2 is 8, so 8 pi divided by 3 radians as my period. And that is what we found over here. So what is my rule for calculating the period of a function? That is going to be the following. So period equals 2 pi divided by b, whatever b ends up being. This right here is my rule. That's how you calculate your period. So the period equals 2 pi divided by b. So the period length of your sine or cosine function is going to be 2 pi divided by b, and that is how far does it take my function to complete one of its patterns, or one revolution of the circle that corresponds with it. If I were to switch this to cosine, just to switch it up, right? Because cosine starts here instead of starting in the middle. When I make this, right, it's the same effect. It's going to have the same effect. But instead of us saying, okay, let's put it all back to the standard, right? We start at 0, 1. We go down to the minimum and back to the maximum, right? Our starting point is the maximum height. So if we start at the maximum, we're going to go down to the minimum and then back to the maximum. That's our checkpoint that we're looking for. And so we change b and we make it, let's make it 2. Well, our maximum's here, our minimum's here, all our values, and we get back to our starting point, and it's pi. Oops. pi is my period. That's how long it took for me to go down, back up. So same idea applies to what I was just doing. It's always going to be this rule. The period length is equal to 2 pi divided by b. So you are going to have an option to work on the worksheet, which is kind of the second half of the worksheet that we gave you guys the other day. And your job is going to be to practice graphing some of these functions and practice figuring out what is the period, what is the amplitude, what are the maximum and the minimum values for these examples based on the function that we give you, based on what parameters are placed on it, determined by what A, B, and C are. So definitely play back this video as you need to calculate your period length, and look at the terminology, look at what happens when I make A negative, it's reflecting it, which is all good and dandy. You just have, okay, now I'm looking at, this is my starting point, because I'm on my y-axis, I'm at 0, comma, -1, go up and back down to my starting point. It's all about your point of reference, What's the perspective that we're viewing this in? So anywho, this is probably a little bit long, but that concludes this. We've covered all three parameters now, A, B, and C, what effect they have on the trig functions. Now it's your job to go practice how to graph these and how to figure out what these new terminology pieces are. Thanks, guys.